or Team 1936, Additive Manufacturing, Optimized Particle Size. Now I'd like to go ahead and introduce our team. My name is Hudson, Engineering Management Student and Project Lead. Next we have Devin, Mechanical Engineer, Jesus, Mechanical Engineer, Aiden, Mechanical Engineer, and Justin, Material Science Engineer. Now I'd like to go ahead and walk you through a little bit of the 3D manufacturing process. Metal 3D printing has 4 simple steps. First, powder selection. Once the powder is selected, then the powder is spread inside the machine. Once the powder is spread, then a laser is applied. And the 4th step is simple. It just repeats step 2 and 3 until a form or object is created. Here's a little video to demonstrate this process. The lasers are moving about a thin layer of powder. Once the first layer is completely burned or melted using the laser, then the recorder comes through and lays a fresh, thin layer of powder. Now that the basics of metal additive manufacturing is understood, we'd like to briefly describe the problem that Honeywell posed to us. As you saw back in the steps of additive manufacturing, the first step is particle size selection. It's well known in the industry that particle size distribution affects residual stress or distortion of the parts being made. Our original project scope was to characterize the effects that particle size distribution has on residual stress. Our team then broke down the effects it has on residual stress into 3 system requirements that we verified by analysis. First, density. Second, melt pool. And third, stress. As our project looked to characterize how these 3 factors, packing density, residual stress, and melt pool, all fit in together to better understand particle size distribution and its overall effect on additive manufacturing and residual stress, our team then broke it down into our system block diagram. It's very simple. The industry typically uses 15 to 45 micron powder range. However, as the industry is so new, a greater experiment needed to be performed to better understand what particle size distribution actually does. Our team set out to first order a batch of powder of 15 to 105 microns. We then set up a sieving process to put us into ranges. We'll talk about this sieving process later in the presentation. Once the powder is sieved, as our system block diagram indicates, we then take it and do a packing density measurement. We'll talk about that further. Once the packing density measurement is taken, we then run it through ImageJ software to do a particle size distribution. From there, the powder is then actually put in to a 3D manufacturing machine where we design and build very specific bars for analysis. Once these bars are printed, we sent the bars up to Honeywell so that they could be cut with their EDM cutter. Once these parts were sent back to our team, we then analyzed them, again using ImageJ software, to characterize the residual stress by looking at the deflection in these printed beams. Once the deflection was looked at in these beams, we then cut them into small pieces, looked at the cross section to understand the melt pool. Once this was done, a final data analysis and correlation test was compiled to give us a final report. Now, our team is going to walk you through the specific steps to make this project happen.
First, we want to take a look at the variables that we can control. We want to make sure that these variables have statistical relevance on the whole project and that they affect what we need to affect. So we decided to look at particle size distribution as our main focus. This is because we are trying to understand how particle size distribution affects residual stress. So we wanted to be able to control particle size distribution in such a way that we can more adequately understand what's going on. So we determined that we want to take a distribution and try to cut it down to its center, starting from the edges and then working our way in. This way, if we had knowledge about the distribution as a whole, that we can cut it down and still have some knowledge about what's going on.
The model we are testing is as follows. Residual stress in metal 3D printed parts arises from uneven cooling due to temperature gradients in the melt pools of the material as it is being built. Higher melt pools allows higher temperature gradients, which causes more residual stress to form. The height of these melt pools is largely determined by the packing density of the powder used to make these parts. More densely packed powders will be able to absorb more energy and cause smaller melt pools than more loosely packed powder. The particle size range of this powder, called the particle size distribution, will determine what this packing density is. Because smaller particles will be able to fill the void between larger particles and take up more space, we believe that more widely distributed powders will have a higher packing density than narrower distributed powders, which will give them a smaller melt pool and less residual stress in the part. For this reason, our team is planning to use these 6 different powder ranges in order to test this hypothesis. The first four are Gaussian distributions with a narrowing width, but the last two are bimodal distributions, with the smaller particles being strategically chosen to fit within the interstitial sites of the larger particles. By using scanning electron microscopy as well as image analysis, we are able to verify that after sieving we have indeed created the desired powder distributions. The packing density procedure involves a simple measurement of the powder's weight and volume. The packing density, as well as the error in our measurement, is able to be determined this way.
To verify the particle size distribution of our selected ranges, we take a sample, run it under the SEM, gather those images, and put them into ImageJ, which is an image analysis software. ImageJ calculates the number of particles and the area of each individual particle. From there, we can determine the distribution of particle sizes within each range and verify that the sieving process has gone properly. For the geometric measurements of the bar, we take a ruler and place it on a flat surface parallel with the top face of the bar. From there, we take an image of that and import it into ImageJ.
For the residual stress model, we have utilized beam theory of simply supported cantilevers, specifically a cantilever with a concentrated moment. This model does have some assumptions. This model is assuming that the deflections are small enough such that the beams are only experiencing elastic strain. This model is also assuming that the beams are isotropic and that there are no flaws such as cracks or pits throughout the material. Using the measured deflection or bend in the beam, we can determine a residual stress. To start, we determine a concentrated moment from the deflection. In order to do that, we have inverted a well-established beam theory deflection formula to solve for the moment that would cause such a deflection. We can then use the moment to calculate an axial stress. In order to calculate the axial stress from the moment, we have implemented the flexure formula to solve for the maximum axial stress. This maximum axial stress is our residual stress.
To analyze the data that we had, we want to take the two variables that we were after and see if there was any correlation. That is, particle size distribution and residual stress. Since 5 of our distributions had the same center point but different ranges, we decided that we would plot the ranges on the x-axis and plot the residual stress on the y. This would give us an idea of the correlation between the two, if any, though it is possible that there would be none. It's just not something that we would see. As well, we wanted to be able to see if our other ideas, our perfect blend of the 80-20 and our idea of the 50-50, had any impact. So we would plot the residual stress on the y-axis, but on the x-axis, we would just have the names of the distributions that we were testing.
After the beams are cut, we are able to measure the melt pool depths by looking at the cross-section of the parts under SEM. The parts are taken through a grinding, polishing, and etching procedure for 316 stainless steel and are observed under the electron microscope to measure the melt pools.
Through the research of this project and the prototypes that we conducted, we have learned a lot about particle size distribution and how it may affect residual stress. We have found that there may be a theoretical perfect blend that, when used in additive manufacturing, can make for stronger builds.
Our final project deliverable is a comprehensive report that fully outlines and characterizes particle size distribution. With the findings in our experiment, Honeywell is able to make calculated and precise decisions as to what particle size distribution they use for their metal additive manufacturing process.